Hello, my dear student. Welcome to another edition of your mathematics lesson. Today, in continuation with your many topic sequence and the series, what you are going to learn today is the second types of sequence, that is geometric progression, the GP. So let's begin. After completing the very lesson today, my dear student, will be able to find and write out the terms in this GP sequence. This is what I hope you'll be able to do after completing the very lesson today. So, my dear student, in your favorite segment of the lesson, Mars Expanded, today I'm happy to give you another group of prime numbers. And this group of prime numbers are called the naughty primes. I'm going to explain what group of prime numbers that are called naughty after completing my lesson today. So, be with me. To begin the lesson, my dear student, let me first explain the second type of sequence, that is the GP, geometric progression. This sequence is a sequence whereby each term after the very first term is obtained by multiplying the preceding term, that is the term behind, by a constant number. So we now use the constant number to generate all the terms, and what we keep doing is to multiply the present term by that very constant number. It will give us the term in the next position. That constant number being multiplied is called the common ratio. And this common ratio simply refers to the ratio between any two successive terms. That is, the result after dividing two successive terms is called this common ratio. The common ratio is usually denoted by small letter r in the formula. Let's just take examples of this GP. Example number one, we have the sequence 1, 3, 9, 27, 81, and so on. This is a GP because looking at the terms, it is multiplication by 3. That is 1 times 3 gives you the next term, which is 3. 3 times 3 gives you the next term, which is 9. 9 times 3 gives you the next term, which is 27, and so on. So in this case, it is multiplication by this constant number 3. So this is a GP. Another example of GP, you have 40, 20, 10, 5. This is also a GP because if you look at the terms critically, you can see it is multiplication by 1 over 2. Multiplication by 1 over 2 is just like dividing by 2. So 40 multiplied by 1 over 2 gives you 20 the next term. This the 20 multiplied by 1 over 2 gives you the next term, which is the 10. And the 10 multiplied by 1 over 2 gives you the next term, which is 5. So multiplication by 1 over 2 is simply the same thing as division by 2. So this is a typical examples of the GP. So let us move. So what we're going to learn next in this lesson as far as GP is concerned is the term of a GP. That is how to find the term at any position in a given GP. So let's say the terms Tn, that is the term at the position R of a GP, is given by this simple formula. This is the formula says Tn, term at any position n equals to A multiplied by R raised to the power of n minus 1, where A is the very first term of the GP, R is the common ratio of that very GP, and n is the position of that very term. So if we asked, for example, to find the term number 80, that are given a GP, and that GP has only maybe first 4 terms there. So you don't have to write all the terms up to that term number 80. Then you now check what is the term there. So you simply substitute in this very formula the first term of that GP, the common ratio of that very GP, and the n with that position of the term that you wanted to find. After simplified, whatever you have finally is the term at that very position. We are going to take examples how we can make use of this very formula to find the terms at any position of a GP. So let us move. Example number 1 says find the 12th the term of the GP. This is just the first 3 terms of that GP. You have 1 over 4, 1 over 2, 1. These are just the first 3 terms of this the GP. We have to find the term number 12 of this very GP. Solution to this very problem, what we do first is to write down the formula for finding term at any position of a GP. The formula says the TR equals to A multiplied by R raised to the power of n minus 1, where A is the first term, R is the common ratio, and n is the position of that very term. So there from this GP, I will now find what will be my A. My A is 1 over 4, the very first term of the GP. and the R, the common ratio. What you now do, you take two successive terms and divide. So I'll now take a second term divided by the first term. Let me do that. That will give me my R, the common ratio. So I'm going to have 1 over 2 divided by 1 over 4. You can take any two terms, but the one divided by the one behind it. This is the rule. So dividing 1 over 2 by 1 over 4, let me change this division to multiplication. So you have 1 over 2 multiplied by 4 over 1, and this gives you finally 2. And the error is now 12 because I'm asked to find the term number 12. So let me go and substitute in this very formula. So I'm going to now have, instead of Tn, I'll now write T12. That is term number 12. This will now be equals to A, which will now be 1 over 4 multiplied by 2 raised to the power of 12 minus 1. I have replaced this R by 2, N by 12. So I'll now simplify this. So I continue. So I'm going to have 1 over 4 multiplied by 2 raised to the power of 11. 11 is 12 minus 1. So I'll continue. So what I'm going to do next is to now multiply this 1 by 2 raised to 11. That gives you 2 raised to 11 over this 4, which now change it to index form 2 raised to 2. Then you can now apply your log indices. You have two index numbers and you want to divide them. They have the same base 2. So there, according to the law, says 11 minus the 2. That is the power 11 minus this power 2. That gives you 9, 2 raised to 9. And the 2 raised to 9 is nothing but 512. So this is now going to be term number 12 in this GP. Let us move and take another example. Example number 2 says find the first term of a GP whose the fourth term is 40 and the common ratio 2. Solution to this very problem, writing down the formula for term in a GP, Tn equals to AR raised to the power of n minus 1. Here I have for the term meaning term number 4, and it's given as a 40, and the common ratio of that GP is 2. What we have to find is the first term. So there, a question mark, the very first term is what we would like to find, and the term number 4 is 40, and R is now 4, R is 2. So I'll now substitute all those in this very formula. So I'm going to have T4 instead of Tn, T4. That will now be equals to A multiplied by 2. That is my R. Look at it here. I replace the R by this to 2. Then R raised to the power of n minus 1 now becomes 4 minus 1. I replace the n by 4. So I continue. But this, the term number 4 is given in the question. Look at it, is 40 for the term. So I'll now replace it. So I'm going to have 40 equals to A times 4 minus 1 gives you 3. So you now have 2 raised to the power of 3. So I'll continue. So what I'm going to do now, this to 2 raised to 3 gives me 8. So I'm going to have 40 equals to 8 times 2 raised to 3. So this 2 raised to 3 is 8. So you now have 8A. So next to find A, you now divide both sides by this coefficient of A, which is 8. So after division of 40 by 8 gives you 5. So your very first term of this GP is now going to be 5. So let's just move and take another example. Example number 3 says find the common ratio of this GP whose the first term is 3 and the sixth term of the GP is minus 1 over 81. Solution to this very problem, always we write the formula for finding a term at any position in the GP, that is the Tn equals to AR raised to the power of n minus 1. So there we now find what is given in the question and what we asked to find. We asked to find the common ratio. But the very first term of the GP is 3. Whose first term is 3? Look at it. And the term number 6 is minus 1 over 81. So T6 equals to minus 1 over 81. And the end there is 6, and we asked to find R. So substituting these values in here, I'm going to have T6 equals to AR raised to the power. I have just replaced the N by 6. So I have 6 minus 1. And 6 minus 1 gives you 5. And now replacing this T6 by minus 1 over 81 there, I will now have minus 1 over 81 equals to 3. That is your A multiplied by R raised to the power of 5. The power of 5 is now from this 6 minus 1. So I'll continue. So what I'm going to do next is to divide both sides by this 3. So I'm going to have minus 1 over 81 times 1 over 3. This times 1 over 3 simply means the division by 3 equals to, so after dividing the right hand side by 3, you now have r raised to the power 5 left. So I'll continue. So I'll now multiply 81 by 3. To multiply 81 by 3, the result is now going to be 243. So you now have minus 1 over 243 equals to r raised to the power 5. So what I'm going to do next, I will now convert this to 243 to indexed form. That, if done correctly, you now have 3 raised to the power 5. 3 raised to 5 means 3 times 3 times 3 up to 5 places, and it will give you exactly 243. So I'll continue. You have 3 raised to the power 5, and this one, if I raise it also raised to the power 5, is still 1. So I can now factor this power 5 outside in the bracket. I'm going to have minus 1 over 3 in the bracket, and that bracket raised to the power 5, because if 5 this goes to 1 raised to 5, 3 raised to 5, the 1 is still 1. So I now have index equation in which the powers are equal. So surely the bases must also be equal. So if the powers are equal, then the bases must be equal. So there I can now say that my R is now minus 1 over 3. This is the common ratio that we asked to find of this very GP. So let's just move and take another example. Example number 4 says that the second and the fifth terms of a GP are 12 and 324 respectively. The question asks is to find its first 5 terms. Solution to this very problem, writing the formula for the term at any position in a GP. So TR equals to AR raised to the power of n minus 1. So what I'm going to do, I have term number 2 and term number 5. So I'm going to substitute so that I have two simultaneous equations that I'll solve simultaneously to get A and R. So term number 2 is given as 12 and the term number 5 is given as 324, but we don't know A and we don't know R. So substituting this in this very formula, I now have T2, that is term number 2, to be equals to AR raised to the power of 2 minus 1. 2 minus 1 simply gives you power 1, so you now have 12 for this T2 equals to AR. Let me just call this equation 1 because I'm going to have another similar equation, number 2, that I'm going to solve together with this simultaneously. So I have 12 equals to AR. So I'll now move and substitute the term number 5 in this very formula. So I'm going to have T5 equals to AR raised to the power of 5 minus 1. I have replaced the n by 5. 5 minus 1 gives you 4, and replacing this T5 by 324, you now have the second equation, 324 equals to AR raised to the power of 4. This is my second equation. It is these two equations that I'm going to solve simultaneously to get A and R. So in attempt to do that, let me just divide the equation 2 by equation 1. This is my equation 2. If it is divided by this equation 1, you see A will now go. So I'm going to have 324 divided by 12. That is the left-hand side of each equation divide each other. Equals to the right-hand side also AR raised to the power of 4 divided by AR. Look at it. So with this, A will now cancel, and R raised to 4 divided by R raised to 1 gives you R raised to power 3. And dividing 324 by 12 gives you 27 equals to R raised to the power of 3. I repeat, A cancel A, R raised to 4 divided by R raised to 1. It what gives you this R raised to the power of 3. So what I'm going to do next is to get the cube root of both sides. That will give you R as 3. Cube root of 27 gives you 3. So what I'm going to do next is to substitute this value of R by 3 in any of the equation to obtain your first term, that is A. So substituting R equals to 3 in equation 1. Look at equation 1. 12 equals to A times R. So I'm going to have 12 equals to A times 3. I have replaced the R by 3. So A times 3 gives you 3A, and divide both sides by 3. You now have A to be equals to 4. So your first term is 4 and your common ratio is now 3. So the question says we are to now write the first 5 terms of this very sequence. So let me just move. The very first 5 terms of this sequence is now going to be, you have the very first term which is 4. Let me write it. This is 4, the very first term. Then to get the next term, you now multiply first term by the common ratio. The common ratio is 3. So 4 times 3 will now give you 12. 12 will now be the next term. Then the third term, you now multiply this 12 by the common ratio, which is 3. So 12 times 3 gives you 36. So 36 is the third term. And next term, you now multiply this 36 by 3. That gives you answer 108. Next term is to multiply 108 by 3. That gives you answer 324. You can see the fifth term given in the question. You can see also the second term 12 given in the question. So this is how we now answer these questions. So with this, I have come to the end of this very lesson. My dear student, I hope you find it resourceable. And let me just move quickly to the last segment. Maths is fun, and I explain what group of prime numbers are called naughty primes. So it says naughty primes have more zeros than any other digit in the number. So those prime numbers that contains zeros, when compared to other digits in the number, they have more zeros. It is those prime numbers that are called naughty prime. Examples of naughty primes, you have this 10,007. This is a prime number, and you can see it's zeros that is dominating other digits. Another naughty prime number you can see is 10,009. You can see about 3 zeros. So zeros dominate other digits in this very prime number. Similarly, you have this 40,009. You can see many zeros there. You have 70,001. You can see many zeros. These are what we call the naughty primes, and many more prime numbers that have zeros dominating all other digits. Those type of prime numbers are called the naughty prime. We see more of these interesting things in mathematics in our subsequent lessons.